Okay, we are beginning our unit on forces, and the place that we always start this, because it's the place that makes the most sense, is with Newton's three laws. These are three laws, and the order isn't important, but I still want you to know it. First law should be familiar. An object in motion or at rest tends to stay in motion or at rest unless an outside force acts on it. That's what it says in books, and that's fine, but it's not very sensible. So, and we kind of already talked about this with momentum, but motion remains constant if the net force acting on an object is equal to 0. Okay. So what that tells us about mass it is the nature of all matter to resist changes in motion. If we remember our Bill Nye, we know that matter's resistance to a change in motion is inertia. For a physicist, inertia, and well, for everybody, but this is how we think of it, mass and inertia are the same thing. So if someone were to ever ask you what inertia is measured in, you say kilograms. That's just how life goes. But motion remains constant if the net outside force acting on an object is 0. The second law tells you what happens when force acts on an object. The acceleration of the object is directly proportional to the force acting on the object and inversely proportional to the mass. That's how Newton worded it. Basically, this one says forces are the things, and really we could say net forces, are the things that accelerate objects. The more inertia we have, the more mass we have, the smaller the acceleration. The more force we have, the larger our acceleration. This is the idea that we use to do the majority of our problems. And then the third one, for every action there's an equal and opposite reaction. The important part of this is that it tells us that forces occur in pairs. If you push on something, that something pushes right back on you. So there are a couple of different ways that this plays itself out as far as misconceptions go. The first one, let's say you are driving your poorly drawn car 100 meters per second, 220 miles an hour, and there's a bug. Okay. When you hit the bug, both you and the bug experience a force. Newton says the force between the two of you is going to be the same, and that's true. Your mass is very large, so you experience a very tiny acceleration or a very tiny change in motion, whereas the bug has a very tiny mass and experiences a very large acceleration or a very large change in motion. The forces on the two are the same, but a 1 Newton force to a bug is a big deal, gives it a big acceleration, and a 1 Newton force to your car is not a big deal and gives it a tiny acceleration. The things that we feel in everyday life are not forces. Our bodies are not good at experiencing forces. Our bodies are, however, very good at registering accelerations. Forces and accelerations are not the same thing, and masses make up that difference. The other way that this becomes a misconception, and we talked about this last year, let's say we have a cart, which is a box on wheels, and there's a horse pulling that cart. That's a horse. It's not really a horse. So, if the horse pulls forward on the cart, force the horse, and the cart pulls backward on the horse, these two forces are equal and opposite, cancel each other out, and nothing moves. Well, it doesn't work that way. All that matters for the motion of the horse are the forces acting on it. And that includes the friction between the ground pushing the horse forward and the cart pulling the horse backwards. It's that unbalanced that determines if the horse moves. So only forces acting on objects matter. Forces that the object apply to something else don't matter at all. So, it's a quick look back on Newton's laws. Next thing we're going to talk about is weight and the normal force. Weight is a common term that we use all the time. By that we mean the force of gravity acting on an object. Force of gravity on a mass. So, if we just have a ball of mass m hanging out, the force of gravity, well, and we drop it, we know that it's going to accelerate at 9.8 meters per second squared. So the force acting on it is going to be the mass of the ball times that acceleration from gravity. That's the force that we get from gravity. The ball will fall at 9.8 meters per second squared. If, however, we put that ball on a table, did we take away what gravity is doing to it? No. We still have the weight of the ball, the force of gravity, mg acting on it. But at this point we also have another force pushing up on the ball. The normal force. It's a surface force. In this case, it's the force keeping the ball from falling through the table. Now, what this does, if we look at both of these forces, the normal force minus the weight, they cancel out, give us 0, telling us that the ball doesn't accelerate. So the net force acting on the ball is 0. We don't go anywhere. And in this case, the normal force is equal to the weight. So, weight is the force of gravity. Normal force is, when we're on a level surface, equal to the weight. The normal force can change and get tricky when we're on an incline. We'll save this just for a couple of days. But when we're on an incline, the normal force pushes normal or perpendicular to the incline, whereas gravity still pulls, it's not straight down towards the center of the earth. So it changes. We're going to have to do some vector math with that. So the question that you all hated last year had to do with a bird and a hand. And it asked, what is the reaction force to the weight of the bird? And instead of trying to discuss that on the video, we will discuss this in class tomorrow. Hopefully only 2 or 3 of you should be really pissed off about the answer. We'll see what happens. Okay? Alright, last thing I want to talk about is friction. Because we covered this last year, friction's an easy thing. It is a force that opposes motion between two surfaces in contact. So, if I have a mass, let's say of 30 kilograms, and we're on a rough surface, the weight of that mass, 300 newtons, it's mg. The normal force on that level surface is going to be 300 newtons. And let's say I pull, with 100 Newton force. Just a gross number. Now, if there's no friction, that thing's going to accelerate 100 newtons times 30 kilograms. If, however, we have a coefficient of friction of 0.5 between those two surfaces, we're going to have a frictional force. Calculating the force of friction is easy. It's our coefficient of friction times the normal force. So our force of friction is going to be 0.5 times our normal force, 300 newtons. Force of friction in this case comes out to be way too big, 150 newtons. If the force of friction is 150 newtons, or can be 150 newtons, and I pull with 100 newtons, is the box going to move? No, the box isn't going to move. I'm not pulling hard enough to beat friction. So in this case, what's the force of friction acting on the box? Oh, having trouble with the pen. 100 newtons, opposing the motion of the box up against the ground. We'll discuss that in class tomorrow, and we'll discuss the difference between static and kinetic friction. That's it for tonight.